with a copper coating. So if you take a penny and you split it in half, you'll see there's the middle part is silver because it's made of zinc. And then, so a lot, like I said before, a lot of transition metal compounds form these really nice colors. So in this case, copper 2 salts are usually blue. So especially like your copper nitrate and your copper sulfate. So any questions about this before we move on to the problems? Nope. Okay. So I'll give you guys maybe 5 minutes to answer this problem set. So just name the following compounds. Okay, so let's go over the answers here. So, okay, so name the following compounds. So the first thing we need to do is to figure out the charge on each of the metals. So in this case, remember this is a very rare hydride anion. So it's 1 minus. So to balance out the 1 minus, the copper needs to be 1 plus. So this is copper 1 hydride. So this is the kind of brownish thing here. So this is a very strange compound. And if I remember correctly, it can be made by reacting something like copper 2 sulfate with hypophosphorus acid. So it's a very strange compound because it's very pyrophoric. So it easily ignites in air. So it's very reactive, very dangerous. Okay, so this one's a little more tricky. So can someone tell me what the charge on the oxygen atom is? So what kind of anion will oxygen form? Exactly, 2 minus. So that means we have 3 2 minus charges. So this contributes 6 minus. So now we have 2 irons. To balance out the 6 minus from the oxygens, what charge does the iron have to be? Great, so 3 plus. So this is iron 3 oxide. So, so the red stuff over here, this is basically rust. This is kind of like rust. Okay, now we have AuCl3. So can someone just tell me what this is? By the way, Au is gold. Exactly, gold 3 chloride. Okay, so this is a little bit of gold 3 chloride dissolved in a little bit of water, and so it has this very nice yellowish color, and you can make gold 3. So like you might have remembered that gold is very unreactive, right? So it's very hard to turn metallic gold into useful compounds. So gold will not dissolve in most acids. It doesn't dissolve in hydrochloric acid. It doesn't dissolve in sulfuric acid. It won't dissolve even in nitric acid. So to dissolve gold, what you need is a mixture of hydrochloric acid and nitric acid, which is called aqua regia. So royal water, because it can dissolve gold. And finally, we have PtCl2. So this one's is platinum 2 chloride. So I want to show you something interesting about platinum 2 chloride. Okay. So, okay. So platinum, it turns out that some platinum salts, some platinum compounds are biologically active. So there's a compound called cisplatinum, which is used to cure cancer. You don't need to memorize this, but it's just a little bit interesting. So PtCl2 and then NH3, 2. So it's just called cisplatin. Cisplatinum. And to make this, what you can do is you can start from platinum 2 chloride. And then this can be reacted with potassium chloride. So you get something like this. Right. And then this can react with ammonia, NH3, to get you your final compound. And the structure is like this. And we will talk more about structures in further lectures. So, and by the way, platinum is just like gold. It's silvery colored, and it's a very expensive and very expensive metal, very rare metal. It's even more expensive than gold. So, kind of interesting how such an expensive metal, which is used in jewelry, also is used to cure cancer. Okay. So now we can talk about polyatomic ions. This is the hard part of the lecture. So eventually you will have to memorize this table and maybe a little bit more. But for now, you can just refer to this table when you need to. So what are polyatomic ions? So these are ions that consist of multiple elements bonded together. So for example, here I have a picture of the nitrate ion. So we have a nitrogen atom bonded to 3 oxygen atoms. And overall, this has a 1- charge, as you can see here. So nitrate. Okay. Now this might seem like a lot to memorize, but there are some tricks to help you memorize these. So to look at some of these tricks, we're going to look at some of the chlorine oxoanions. So by the way, a lot of these polyatomic ions have oxygen in them. For example, manganate, permanganate, phosphate, sulfate, nitrate, and carbonate. So these are called oxoanions, which I will write down. So these have some formula like X, O, Y, and minus, some general formula like that. Okay. So chlorine forms a lot of different oxoanions with oxygen, all of which are 1- charge. So how do we name these? So first of all, we start with chlorate. So this has 3 oxygens. Now what happens when we add another oxygen, right? So here we have 4 oxygens instead of 3. So this is called perchlorate. And the reason why it's called this is because per is a Latin prefix and it means complete. So this has the complete amount of oxygens. Kind of makes sense? Okay. So if we have 1 less oxygen, so 2 is 1 less than 3, it's called chlorite. So notice the chlor part remains the same, but we change the ate to an ite. Okay? Okay. And then if we have even 1 less oxygen than that, ClO minus, it's hypochlorite. So hypo is like a prefix for like less, so like hypothermia, right? So yeah, so the hypo salt will have the least oxygens. So just to say, so what do these do in our daily lives? Okay. So the space shuttle, see these little white boosters on the side of the space shuttle? So those are filled with ammonium perchlorate, I think. And ammonium perchlorate reacts very violently with aluminum to form aluminum oxide, which is which propels the space shuttle. So this is a little bit kind of funny. So sodium chlorate. So back in like the 30s, the 1930s, in New Zealand, some farmers were reporting that their pants were exploding because the government recommended that they use sodium chlorate to kill weeds in farms. But the problem is that sodium chlorate will react with organic substances, for example, the cotton in your pants. So because of this, we got reports of exploding trousers in New Zealand in the 30s. Okay, what about chlorite? So here is a jar of sodium chlorite, and this is used in the industry to bleach paper. So this is what makes your paper white. And then finally, we have hypochlorite. So this is just common household bleach. And yeah, so common household bleach is a 5% solution, I think, of sodium hypochlorite. Yeah. So you can see this pattern show up again with these oxo anions. So we have sulfate with 4 oxygens. And then if we have 1 less oxygen, we have sulfite, right? So the 8 turns into an ite, just like chlorate and chlorite. Okay, now you might be wondering about the little bi prefix here. So the bi prefix means that there's 1 hydrogen atom there. There's a hydrogen atom there. And this hydrogen is kind of like, you can think of it as like an H plus. So that means it changes the charge from 2 minus to 1 minus. Because like a 2 minus charge plus a 1 plus charge is a 1 minus charge, right? Okay. So again, we have bisulfite here. So the bi doesn't mean 2 sulfurs. It means a hydrogen, okay? Which is kind of confusing, but yeah. So I'll give you an example. Let's do kind of an example. Okay. So PO4, 3 minus, is called phosphate. Okay. And then so by the way, for now, just ignore the hydrogen. For now, ignore the hydrogen. So can someone tell me the name of this ion? This one. So notice we have 1 less oxygen, right? So we take this part, remains the same. And the 8 turns into an ite. So this is the phosphite anion. So here's a minor point. This is a little confusing. And you should probably ask your AP chemistry teacher about what they want. So in a lot of textbooks, and a lot of like AP chemistry textbooks, I see PO3, 3 minus written. The problem is that this doesn't actually really exist, at least in what I found in the chemical literature. In aqueous, so in water-based solutions, so when we're talking about like this stuff dissolved in water, this does not exist, and it will be HPO2 3 2 minus. And the reason for this is because the structure looks like this. Then there's an oxygen here and an H. Right, so the structure kind of looks like this. Right. So phosphorus, the oxygens, and the hydrogen. And this, you cannot remove this hydrogen in aqueous conditions. So phosphite does not refer to PO3 3 minus. It instead refers to HPO3 2 minus. But this is a bit of a strange point, and you should probably ask your AP chemistry teachers for clarification on what they want on their tests, okay? But what I'm telling you is basically correct. This is not fake news, okay? So just to drive the point home, what about this? What do you think the name of this ion is? No. So it has 1 less oxygen than phosphite. So we write phosphite, and then we put the hypo prefix in front. Right, so this is the hypophosphite ion. And again, if I draw the structure, it looks like this. And these hydrogens cannot be removed under aqueous conditions. But yeah, so very strange stuff. And what else? Okay. Now here's, okay. So remember I was talking about the bi prefixes. So not everyone uses that nomenclature. So sometimes that stuff like this this can be either bisulfite or um, or hydrogen sulfate. Okay. So either one of these is perfectly acceptable. For phosphate, however, we have a lot of different forms. So we have these three forms. And so this means that you cannot use the term biphosphate because you don't know whether it refers to this or this. So this is usually called hydrogen phosphate. And this is called dihydrogen phosphate. Okay. Does anyone have any questions about that? Nope. Okay. So for now, don't really worry too much about memorizing these. It will come to you eventually, and working through the homework problems should help you. Okay. So can you name the following? Oh, and one minor note. So when we named compounds made from these more complicated ions, the naming rules are still the same, just cation before anion. So, for example, okay, so the cation is just ammonium, and this is carbonate. So the name is just ammonium carbonate. Okay, so not too complicated. So how about I'll give you 5 minutes to name the following compounds. And okay. How about how about everyone takes a screenshot of this table or take a picture of this table, just use your phone or something like that. And that way you can solve the following problems a bit more easily. Or you can go on Google and look up common polyatomic ions. Okay. So I'll just give you a minute to do that. And just type in the chat when you're good. Okay, so Ethan and Brian, have you got what you need? All good? Okay. So just look up common polyatomic ions and yeah. Okay, so now I'll give you 5 minutes to name the following compounds, or a few minutes. Hopefully it won't take too long. Okay. So let's try to get the last two. Okay. And then just and now we just need the last one. So. Great. Okay. So we got all of them, and they're all right. So, and I can just talk a little bit about these compounds. So first we have magnesium sulfate. So this stuff over here. So has anyone heard of Epsom salts? So Epsom salts are magnesium sulfate, and a lot of people put them in baths for some reason. I don't know why. Maybe it makes them feel better. Okay. Next, we have ammonium nitrate. So under standard conditions, ammonium nitrate is perfectly stable. However, it is explosive if you like hit it with like hammers or if you put it in a fire. So does anyone know what picture this is of? Just out of curiosity. It was on the news a few years ago. Yeah. So this is the Tianjin explosion. So Tianjin is like a city very close to Beijing, so like a port city. And so this was an industrial accident. So they had a big ammonium nitrate explosion. So there was this huge fireball and it was in the news and yeah, very bad. So, okay. So next we have potassium permanganate. So potassium permanganate is this very beautiful purple substance. So I've used it before. So it's very dark purple, very strong purple. And so it's a very strong oxidizing agent. So it really likes electrons. And it's actually used as a disinfectant. So it has some use in the medical field. And then finally, we have ammonium chloride. So ammonium chloride and other related substances like ammonium carbonate are used as smelling salts. So basically so you just smell them and they're supposed to like wake you up or something like that. So basically how they work is they release ammonia gas. So this ammonia gas goes into your nose and it reacts in your nose with water to form ammonium hydroxide, which burns your nose, and apparently that helps you wake up. So in sports, believe it or not, in sports people use these. So if you see like hockey players on the sidelines sniffing little pouches of salt, it's ammonium carbonate or something like that to get people more active. Yeah, I know, right? So very strange. Okay. So now, our final topic, but probably the most important topic. So if I give you a name of a compound, how do you determine the chemical formula of that compound? So here are a few steps. So first, you need to identify the cation and the anion. So break up the form. So give it a name. Determine what component is positively charged, what component is negatively charged. So in this case, we're using calcium chloride. Oops. Okay. So now we use the crisscross rule. So what is that? So we write the charges. So from before, we know that calcium is 2 plus, and then chlorine is 1 minus. So what we do is we use the crisscross rule. So this 2 goes to here, and this 1 goes here. So it's Ca1, Cl2. Okay. Now, sometimes we need to divide by the greatest common factor. The greatest common factor of 1 and 2 is 1, so we don't need to do anything. And then finally, we check to make sure the total charge is zero as a double check. So calcium, 2 plus, times 1 is 2 plus. Then Cl minus, 1 minus, times 2 is 2 minus. Those sum to 0, so we're good. And then finally, we omit the 1 since the 1 is implied. We don't need it. Now, let me do an example. Iron 3 phosphate. Okay. Okay. So, can someone tell me what the cation is? What's the formula of the cation? By the way, iron is Fe. Okay. So let's do step by step. What's the charge on this iron atom? What's the charge? Great, 3 plus. So remember, it's just the Roman numerals. 3 plus. And then, can someone tell me the formula of the anion? You might need to look at your table. So phosphate. Great, PO4 3 minus. Okay, so now we need to use the crisscross rule. So we get Fe3, PO4, 3. Oh, and then we write the polyatomic anion in parentheses to avoid confusion, so it doesn't look like 43. And now we need to divide by the GCF. So the GCF of 3 and 3 is 3, right? So we divide by 3. So we get Fe1, PO4, 1. And then we omit the 1. So this becomes Fe, PaO4. Does anyone have any questions? So I'll let you guys write this down for a second. Okay. Now, there's one point about nomenclature that you might need to know. So if you're reading an older text, so an old-fashioned book, you might see the terms ferric and ferrous, cupric and cuprous, and etc. And then maybe even auris or auric, and then auris. Okay, so what does this mean? So when a metal can have 2 possible charges, the higher charge, so two possible charges, the higher charged one ends in ic, and the lower charged one ends in os. So iron, the most 2 common charges on iron are iron 3 plus and iron 2 plus. So can someone tell me which one is ferric and which one is ferrous? Which one of these is ferrous and ferric? Yeah. So remember, the higher charge ends in ic, and the lower charge ends in us. So ferric is Fe3 plus, and then this one is Fe2 plus. Now, copper also has two common oxidation states. So copper 1 plus and copper 2 plus. So this is copper 2 plus, this is copper 1 plus. And then for gold, we have gold 3 plus and gold 1 plus. This is just a minor point. So the most important thing to note is the ferric-ferrous dichotomy. You probably should know that. But yeah, this is fairly old-fashioned stuff, and I don't think modern chemistry textbooks really use this notation. So just something to look out for. Okay, so now this is the problem, this is the big problem set. So I want you to determine the chemical formulas of all of these compounds. And you should have a periodic table with you, right? Right? Okay. So you might need a periodic table, but just work through these. And after a few minutes, I will just go over some of them. Oh, and I provided a very nice table for you here. And it's alphabetical, by the way. Feel free to post your answers in the chat if you want. I'd encourage you to, so I can correct any mistakes. Okay. So I guess you can like hold up with your fingers or something like that. Like how many have you gotten through? Just to get a sense of, right. Okay. I don't know. Do you want me to like do you want me to start going over the answers or should we just keep on going? What would you guys prefer? Okay. So since only one person voted. So okay, so that's what we're doing now. So let's review some of the answers. So okay, let's go. Sodium phosphate. So can someone tell me what the charge on the sodium ion is? Great, 1 plus. Now look at the table. We find phosphate. So phosphate is over here. Remember, this is alphabetical. So phosphate, PO4 3 minus. So we do this plus. So crisscross. So the answer is Na3PO4. Great, and this is used as a fertilizer. Okay, potassium bicarbonate. So can someone tell me what the charge on the potassium ion is? Look at the periodic table. Okay, great. So remember that potassium is in the same column as sodium is on the periodic table. They're in the same group, group 1. So that means they both have the same charge, so they'll both be 1 plus. Okay, now bicarbonate. This is a bit tricky. So remember what I said about the bi and hydrogen thing? So the other name for bicarbonate is hydrogen carbonate. And when we look at that on the little thing, it's HCO3 minus. So when we apply the crisscross rule, you should get KHCO3. So if we replace the potassium with sodium, you get what's called baking soda. So it reacts with acids to produce CO2 gas, which makes your bread rise. Okay. Copper 2 nitrate. Can someone tell me what the charge on the copper is? So remember, the charge is just in Roman numerals. So you don't need to do any yeah. So copper 3 plus is very rare. So if you want to learn more about it, you can read my inorganic textbook. But you're not going to see it in your chemistry courses. So you're right, 2 plus, and then we look at nitrate. So where's nitrate? Nitrate is over here. So when we apply the crisscross rule, crisscross, Cu1NO3 2. So CuNO3 2. So copper 2 nitrate. This is a very strong blue color. It's very pretty. Okay, copper 1 chloride. So the charge is 1 plus, right? And then can someone tell me the charge on the chloride anion? Great, Cl1 minus. So if you look at the periodic table, you need to add 1 electron to get to a noble gas configuration. Argon in this case. So when we do the crisscross rule, you get Cu1Cl1. You omit the 1, so it's just CuCl. And what's a little bit interesting about this compound is it catalyzes a very interesting reaction in organic chemistry. So maybe I can draw it out for you. R, and then you react it with something like this. So R1 and R2 are just the rest of the molecule. And then this forms a, oh, that should be a normal arrow. So this forms a very interesting compound. Let me see if I can draw it. And it looks kind of like this. So, oh, that's not right. Oh, well. Something that looks like this. This double bond should be there, and then that should be an H. So this is called the Huisgen cycloaddition for those of you who are wondering about that. Okay, not super important. Okay. Vanadium 5 oxide. So can someone tell me what the cation is? Vanadium is just a V, by the way. Oh, class will end very soon. Just want to get through this one, and then we can stop. Okay. Okay, so you got the O2 minus part, right? But what about the vanadium? So what charge does the vanadium have? Great, so V5 plus. So we apply the crisscross rule. And that's our answer. And what's the use of V2O5? It's used as a catalyst to make sulfuric acid, which you'll find in your car battery. So that's basically the end of class. Does anyone have any questions before we leave? Like, does anyone have any confusion with any of the material I presented today? No? Okay. Well, feel free to email me questions at any time. My email is alecczzhu@gmail.com. So that's a double C. And so feel free to email me any questions if you need to. And I encourage you to do the lesson 2 homework, which I posted on the Dropbox earlier today. So with that, see you later, I guess. Have a nice day. See you later. Okay. Yep, no problem. Okay. No questions? Okay. Yeah. So have a nice day.